How do we prove the quotient rule? Well, first, we should remember what the quotient rule says. So remember what the quotient rule says. It says the derivative of f over g is the derivative of f times g minus f times the derivative of g all over the value of g, not the derivative of g, just g of x squared. But we haven't actually seen a proof of the quotient rule. Why should the derivative of a quotient be governed by that crazy-looking formula? Well, one way to justify this formula is to combine the chain rule and the product rule. So we're trying to build our way up to the quotient rule, so we can first do the simplest possible case of the quotient rule by hand, if you like. What's the derivative of 1 over x? Well, 1 over x is just x to the minus first power. And if I differentiate this, that's the power rule. We saw how to do that before. That's minus 1 times x to the minus second power. Another way to write this is minus 1 over x squared. Now, if you weren't certain why the power rule held, you could also have calculated this derivative by hand by going back to the definition of derivative. This is actually how we justified the power rule for negative exponents. This limit, you can also calculate, is minus 1 over x squared. Knowing how to differentiate 1 over x is enough for us to differentiate 1 over g of x by using the chain rule. So we're going to use the chain rule. So let me first make up a new function. Let's call f of x that function 1 over x. So then f prime of x is minus 1 over x squared, the derivative that we just calculated. Now if I wanted to calculate the derivative of 1 over g of x, well, that's the same as the derivative now of f of g of x, since I defined f to be the 1 over function. Now by the chain rule, the derivative of this composition is the derivative of the outside at the inside times the derivative of the inside. The derivative of f is minus 1 over its input squared. So f prime of g of x is minus 1 over g of x squared. That's looking good. That's like the denominator of the quotient rule, all right, times g prime of x. So the derivative of 1 over g of x is minus 1 over g of x squared times the derivative of g. Now I've got the product rule. So if I can differentiate f and I can differentiate 1 over g of x, I can differentiate their product, which happens to be the quotient f of x over g of x. So I want to differentiate f of x over g of x, right? I'm trying to head towards the quotient rule. But I'm going to rewrite this quotient as a product. It's the derivative of f of x times 1 over g of x. Now this is the derivative of a product, so I can apply the product rule, which I already know. And that's the derivative of the first times the second plus the first times the derivative of the second. But we calculated the derivative of the second just a moment ago. The derivative of 1 over g of x is minus 1 over g of x squared times g prime of x. So I can put that in here as the derivative of 1 over g of x. It's minus 1 over g of x squared times g prime of x. By rearranging this, I can make this look like the quotient rule that we're used to. Let's aim to put this over a common denominator. So I could write this as f prime of x times g of x over g of x squared plus, what do I have over here? Well, negative f of x g prime of x, the negative 1 f of x g prime of x over g of x squared. And I could combine these two fractions, f prime of x g of x minus f of x g prime of x all over g of x squared. That's the quotient rule, right? We've got to the quotient rule at this point. And how did we do it? Well, think back to what just happened. I used the power rule to differentiate 1 over x. Once I knew the derivative of that, I could use the chain rule to differentiate 1 over g of x. And once I knew the derivative of 1 over g of x, I could then use the product rule on f of x times 1 over g of x to recover the quotient rule. What's the upshot here? Why is it important that the quotient rule can be seen as an application of the chain rule and the product rule? One reason is a pedagogical one. I think it's important for you to see that all of these differentiation rules are connected together. I hope that'll give you a better sense of the rules and make them more memorable.